So now we're able to tell if a salt is acidic, basic, or neutral. Based on that information, we should also be able to determine the pH of a salt. Now, if we have a neutral salt, really easy, my pH is just going to be 7. But if we have an acidic or basic salt, we're going to have to solve an equilibrium problem. The good news is we basically already know how to do this. It's really just a weak acid or base problem, and there's just going to be a couple extra steps involved. The first thing we need to do is what we just talked about, determine if that salt is acidic, basic, or neutral. And then we're going to need to find the Ka or Kb of the acidic or basic component in the salt. So we know salts always have conjugate acids or bases in them, and we're usually provided with the Ka or Kb of the original acid or base. So what we need to do is go in there, is once we figure out the acidic or basic component, figure out its Ka or Kb. So let's look at an example. Determine the pH of a solution that is 0.250 molar in sodium acetate and determine if it's acidic or basic. Well, the first thing we're going to do is determine this second part, is it acidic or basic? So we're going to follow our usual procedure. We have sodium acetate, C2H3O2. We're going to break it apart into its two pieces, the positive piece being sodium and the negative piece being C2H3O2 minus. We're going to figure out what it came from. So this positive piece always came from a base. If we have a metal ion, we just give an OH to it. This negative piece always came from an acid. We always just throw an H in the front. So now we need to judge our relative strengths. So let's remember our little drawing here. So if we have a strong thing, its conjugate is neutral. If we have a weak thing, its conjugate is weak. So we go look at NaOH. This is a strong base. So if we have a strong base, its conjugate is going to be neutral. Acetic acid, on the other hand, is a weak acid. And if we have a weak acid, its conjugate is going to be a weak base. So now we can decide, okay, weak versus neutral, weak wins. So overall, this is going to be a basic salt because it has this conjugate base in there. So first step done, we've determined if it's acidic or basic. Now that we've figured out that this is the basic component, we're really going to ignore the sodium for the rest of the time. It's neutral. It's not doing anything. It's not going to affect the pH, so we don't have to care about that guy. So from now on, we're just going to focus on this C2H3O2 minus piece. So let's start there. We know this is basic, and we know we have C2H3O2 minus. Well, if he's a base, let's write a reaction for him reacting with water. So I'll have a double arrow. This is a base, so it's going to accept a hydrogen. So I'll have HC2H3O2, AQ, and then that'll just leave OH minus behind here. So we've written the expression. Now we need to write an expression for the Kb. That's always the next step that we do. So this is a conjugate base, produced OH minus. We're going to have a Kb, and we just do our usual products over reactants. HC2H3O2 times OH minus over C2H3O2 minus. Now notice it gave us a Ka. It gave us a Ka for this piece, this acid right here. But we need the Kb for its conjugate. So this is where we're going to keep in mind that relationship that Ka times Kb is equal to 1.0 times 10 to the negative 14. So I'm given the Ka, that means I can solve for my Kb. It's just going to be 1.0 times 10 to the negative 14 divided by my Ka, which is 1.8 times 10 to the negative 5. Ooh, can't really see that. Negative 5. And again, that information was provided, didn't just get it out of nowhere. So I can solve for Kb, and if I plug this into my calculator, I find that my Kb is equal to 5.6 times 10 to the negative 10. So this is the second extra step. The first extra step is breaking apart your salt. The second extra step is that you're usually given the Ka or Kb of a conjugate thing, And we have to use this relationship, Ka times Kb equals 1 times 10 to the negative 14, to figure out the Ka or Kb that we're interested in. Now, we still can't solve the problem from here. I want to know my pH, which means I ultimately need to know this OH minus concentration so I can get to a pH. So now I'm going to go ahead and do my usual thing, which is make an ice table. Cross out water because it's a liquid, and fill in my information. I start with 0.25 molar of the salt, and since the salt produces 1 acetate ion, that's also how much of that I'm going to have, 0.25 molar, because as the salt breaks apart, for every 1 salt, we had 1 of these pieces. I'm going to start with 0 of my products. I'm going to use up X and produce X of my products. So at equilibrium, I'm going to have 0.250X. I'm going to have X here and X here. And now we should recognize this as the equilibrium problem we've done a bunch of times before. So we have this Kb expression here. We have these, so we can just go ahead and plug this in. So I'm going to scroll down, give us some more room. So my Kb is equal to 5.6 times 10 to the negative 10. And if I do products over reactants, I have 2 x's, so that's going to give me x squared over 0.250 minus x. And now I'm just going to solve. I see that k is a tiny number, which means that x should be small. So everywhere I've added and subtracted, I can really just ignore that. Then I'm going to move this 0.250 over to the other side. So I'll have 5.6 times 10 to the negative 10 times 0.250 is equal to x squared. And then to solve for x, I just need to take the square root of both sides. So when I do that, I find that x is equal to 1.2 times 10 to the negative 5. I always like to do my 5% check over here. So I take x, which is 1.2 times 10 to the negative 5. I put it over my initial concentration, which is 0.250. It's percent, so I multiply by 100. And that gives me a really tiny number, 0.048%. Certainly less than 5, so I say check. My x is small approximation is valid. So now that I've solved for x, I do what I always do, and I say, all right, I forgot what I was doing in this problem. Oh no. All right, sorry, it erased that, but we can keep in mind x is equal to 1.2 times 10 to the negative 5. Sorry, don't know why it erased all that. There we go. And now we've reached this point, we go back and say, what was my problem asking me for? We say, aha, it wanted the pH. So x really, what I care about was giving me this OH minus concentration. Now I'm going to use that to get my pH. So this x down here was really giving me OH minus. So now I just need to get from OH minus to pH, and I know how to do that. The way I like to do it is to go ahead and get my pOH by taking the negative log of my OH minus, 1.2 times 10 to the negative 5, and that's going to give me 4.93. And then my pH is, of course, 14 minus that pOH, which is going to give me 9.07. So I got my final answer. My pH is 9.07. And if we go back and look, I originally thought that my solution was basic. So now this helps confirm my answer. So we can see pH of a salt solution, really, really similar to our weak acid or weak base. 2 extra steps. First, decide if it's acidic, basic, or neutral. Then you take that acidic or basic part and do a weak acid or base problem. And the second thing we need to do is figure out the Ka or Kb based on the Ka or Kb that they gave you. So remember, these are conjugate pairs. So we can use this relationship right here to find the Ka of our conjugate acid if they give me the Kb of a base, or to figure out the Kb of a base if they give me the conjugate acid. So here they gave me a Ka, and I use that to get my Kb. After that, you just solve an equilibrium problem, go back, see what it really gave you, and use that ultimately to get your pH.